Good morning, everyone. Welcome to another episode of Xah Talk Show. You are watching XahTV, and today's 2021 April and April 12th. And today we are going to do Wolfram language coding. Okay, let me show what I'm going to do. So there is my XR Talk Show topic notes. Okay, that's my random notes on things to talk about. So today I'm going to do probably an hour or 50 minutes, no more. And I'm going to code Mathematica Wolfram language. Okay, so if you have questions about Wolfram language, just shoot. Okay, and am I alive? Check voice, check video, check. Yes, my hands. Look, let me show you my pen spinning non-stop. So this is Kinesis Advantage 2 keyboard. It's a fantastic ergonomic mechanical keyboard and programmable, on-the-fly programmable. This is my favorite, $350, my friends. And the other one you are looking at is Ultimate Hacking Keyboard. I use as a macro pad. For example, last window, back to last window, last window, last window, and let's go to a browser and look at these two. So previous tab, previous tab, previous, previous, previous. So I can just all single key press. Now if you look at this web page, one single key press to magnify, toggle magnify window, and you can see algorithmic mathematical art. Now this is very related to what we are doing today. Mathematica coding. Mathematica can code all of these. In fact, why don't we begin with that? Okay, it's just for I'm coding the Mathematica. I'm going to do some of my. I need to plot and write some programs for my website, but for fun, let's do this one. Okay. So for example, let's see how Mathematica does. Okay, so this is a implicit plot 3D. Let's see if implicit region. Okay, ContourPlot 3D. I believe. Okay, I believe. I'm not sure. I believe this is one. Yeah, this is one. Last time we yeah. Last we haven't showed this one, but so let's do this one. Okay, ContourPlot 3D. And what is the stupid? Mathematica. I think they should have a feature where when you just press tab and it gives you all the template for the arguments. So ContourPlot 3D. What's going on? So you need that. So let's plot that equal. I believe in Mathematica it's 2 equal, 3 equal, 2 equal. Yeah. So x min, x max. Okay. Yeah, I don't want those sub. Okay. Let's do this. Okay. Hold on a sec. Copy. Let's go back to what is this? Let's go back to Emacs. Okay, in fact, I'm thinking of writing a reference link. What's going on? What's pause it. What the? Okay, I don't want that. ContourPlot. Let's just plot it myself. Okay, let's write it. So that's so x from 0, 3 to 3. Okay, and do the same for y and z. Okay, so that is our expression. Copy that and let's go to Mathematica. Let's see what it does. Try it. Options expected. Oh yeah, so we got extra comma. That's not allowed in Mathematica. Now it's plotting. Okay, I don't think this is working. Oh yes, it is. Fantastic. Now you see. Let's see the full glory of this. Okay, so you can see, so I call this thing a Borg cube. Like 15 years ago, Mathematica cannot do this. I believe the first um, version that does this is around 2006. Yeah, so this is fantastic. Actually, I want to increase the resolution. So increase, let's say 326. Okay, change 326. Okay, let's rid of that. Okay, this way it's easier to see. So let's plot another one. Do it. Okay, again you got the extra comma here. Mathematica doesn't like that. Do it. Good morning, potato eater. Good morning, Grim System Admin. Where are you from, Grim System Admin? In USA, I think. So let's see. Let's look at this. It takes a while. So this is Mathematica. You are seeing what? Oh. Okay. Now it's done. Now let's see the full glory. Yeah, what's going on? I want to toggle window. Yeah. So I want to make this big. Okay, so you see, isn't that beautiful? This is the beauty of mathematics. You see, you can just plot random kind of things, and you can observe their structure. So this is called, technically in mathematics, this is called implicit plot of an equation of 3 variables. And any points on the surface is a coordinate x, y, z, and they are a solution to this equation. So in Mathematica, you call this is done by ContourPlot. Okay, so that's that's power of Mathematica. You can if you are industrious, you can write this. You can try to implement this in Python or Golang or whatever. With a graphics library. This is beautiful. That do be a nice cube. Hello, based. Haven't seen you for a while. Okay, so that is one of the things. And again, this is done by Mathematica. This one is by Michael Trott, who is I would say the top expert. Let's put a number. The top 100. Among the top 50, let's see, top 50, okay, or even top 20, master of Mathematica programmer, Michael Trott. He works at Wolfram Research, since 1990s. I met him when I was there. And he is known for this fantastic. This is done back in 1995, by the way. So today you look at this, it may not seem that great, but this is done in 1995, and in fact, so he's he wrote several books, but he's not, if I may say, he's not a great writer. He's his book 1999, this Graphica is like 3 volumes, huge, and the code is impossible to read. Anyway, but this it's an old book, 20 years ago. It's probably not worth it. I don't think it sold much anyway back then. But anyway, Michael Trott. Okay, Michael Trott is the top expert Mathematica programmer, and he was he's a physicist. He's a Russian, I believe, Russian. Yeah, he physicist. That's his background. And also anyway, so I'm starting to talk about lots of these random topic. Well, that's today's, I'm not doing something specific today. Let's try this one. Okay, now remember, you see the graph I have here. You see this one, which I call Borg cube. This is created. This one is plotted by this application called uh, graphing calculator. It's simply just called graphing calculator. It's fantastic. It's if you search for it, there's a very weird, wonderful story. This is an application that Apple Macintosh included in their Power PC around 1995. It's part of the MacOS. When Apple switched from Motorola chip to the Power PC chip around 1995 or 1994, something like that. Yeah. So then Apple macOS included a application called graphing calculator, and this to this day it's a best graphing calculator to this day. Okay, you can find and there's a okay. Let me talk about it. Okay, so let's go to you go to XahTV Math. Okay, go to my website Math. Okay, go to Xah Math. Then you see a bunch of these things. Then you want to go to math software. Okay, then you go to curves and surfaces. Now these are a bunch of great software. I haven't checked for them for a long time. I mean, this is from a professor, my friend, Professor Richard Palais, and this I haven't checked. Anyway, some of them the link might be dead. Last time I checked, this one is there. It is. The personal home site you have requested has been retired. Okay, usually they are PhD students or professors. So okay, the link is done. But usually you can find the new URL by okay. So yeah, so here is a new URL. Spivak. It does differential geometry, this application. Oh, Internet Archive. Okay, yeah. So people moved on, from yeah, yeah. This website actually cites my website for it. Yeah. Anyway, so you go to my website. Sorry, so I need to update this. But anyway, so here is the graphing calculator. Okay, okay. The new name is nuCalc. Now there's an interesting story. Now this application is created by Ron Avitzur, a kind of weird a weird programmer. It doesn't who doesn't work 9 to 5 in in corporations. He's a how do you say hacker types. So he wrote this application. It's not official, but eventually it became. He's got a story somewhere here. If you search for let's see if I have a link. Yeah, graphing. I don't have a link, but he has a story about how he got his application included in Apple, and he wasn't even paid by Apple. That was back then. Um, not like today's how corporation works. Let's see if I can find a story. Maybe this one. The graphing calculator story. Okay, so he did a talk. Yeah, okay. Anyway, he did a talk at Google. That this is 2012. I mean, today's Google is something else now. So anyway, so that is one of the great, this application. The homepage is not very good. It's kind of silly, but this is one man's product. One weird programmer hacker type product. Anyway, that's one of the. I would say it's the best graphing calculator. Okay. Anyway, because I have tried. I have literally tried hundreds literally of softwares that does math since 1990s. So this is my compilation of it, and today I haven't been maintaining them that much because there are so many I cannot keep up, and there are a lot of JavaScript ones. But anyway, this is used to be popular. Anyways, so I was saying, so how did I mention? Yeah, so I was saying this is plotted by graphing calculator, and you can also rotate it in real time. And now let's go back to XahMath. Okay, now let's go back to what I was talking about. Okay, let's restart over. Math, XahMath, algorithms, where algorithmic mathematical art. Now let me explain about this article again. This article. Hello, how are you? I'm good. Hello, Justin Scarfi. So what math have you been doing? Fazin. Hello, Fazin. No, I'm not. Are you do you have a job offer for me? Post private message me. So Justin Scarfi is a mathematician at Canadian University of Vancouver or something, right? Anyway, so back to, so I was talking about by the way, this article, Algorithmic Mathematical Art, I wrote in 2004, which I consider this to be one of my great articles. It does two things. One, it gives you a overview of mathematical art, of different types, different approach. For example, geometric surfaces. That's what you're seeing. This is a Raymond sphere. Let me show you. This is my professor. Raymond sphere. So you are looking at Raymond sphere. Let me show you. Not that's not Raymond sphere. That was the this is Raymond surface. Okay, which is, let me show you. So you have a bunch of beautiful mathematical surfaces. Where is it? Wait, surface, minimum surfaces. Okay, that's Raymond surface is a minimum surface, right? Yeah. So you can, let me turn on JavaScript so you can see. So if you want to get serious about this, you need to study these are part of differential geometry. Okay. So this surface, you are only looking at part of it. It's cut off. So imagine, I have always wanted to do this. Imagine, try to implement this thing in a gaming engine. Like you guys gamers, Unreal Engine or whatever engine. Try to implement this so that you can, for example, become a fly and fly around the whole surface. Now, remember, this surface you are seeing here is cut. It's only part of it. It should be like, it should like partition the plane into like infinite rooms. So it's not like round. It doesn't have edges like that. It just, in order to draw them practically, that's why it's cut like that. But actually, it should just like fill out the 3D space. So what is this one? So this one shows how different surface of this family changes. So this is Raymond surface, and there are so many others. Okay, these are called minimal surfaces. So what I was saying, yeah. So back to this article. So the first part is a outline of all the different mathematical arts. So you can see here's another type. They are related to regular polyhedrons or polytopes. You can see. Then you have plane curves. Different fascinating. Now this is not the boring trigonometry you see in your math classes. When you see this, it makes you want to be a mathematician. But it's trigonometry. This, for example, this one is a trig equation. So let's go back to Mathematica. Let's try plot that. Okay, so let's okay, let's go to ContourPlot This time not 3D, just 2D. Okay, and the equation is that instead of that, comma, and xy. Okay, so let's try that. Back to Mathematica, paste it, run it. Loading Wolfram research server. I don't know why that happens. Now I don't know why is ContourPlot, I hate that. So that means you need to, because ContourPlot should be part of the core Mathematica, as opposed to, requiring to connect to Wolfram server. I thought, anyway. So you see these, okay? So let's try to change the parameter. This is too small. So 6. Let's try 16. Okay. Okay, so this is Mathematica's rendering. Now I want to make some, you might, this doesn't look so good. So you want to increase plot points and things like that. Let's say 250. That should make it, yeah, now it's beautiful. So this is an implicit plot. Each point is x and y, and is a solution that makes this equation true. So beautiful, So back to the, and this image, this one is density plot. This is done in Mathematica, okay. And this one was plotted in, actually it's also plotted in Mathematica. I think I forgot. Anyway, so first of all, this article gives you a outline of different type of geometric artwork. These are inversion. You can study them in geometric inversion, which is not very popular topic. You don't usually learn this in, if you go through math major in college. Yeah, inversion, but they are certainly part of math. Or if you have done complex analysis, then inversion is basically 1 over z. Okay, 1 over the 1 over z. That's what geometric inversion is about. So okay, so inversion. So these are different inversion pictures, and here is a transformation of the plane, and here is a recursive turtle graphics or L systems. Beautiful. This is done in Mathematica, and this is a famous curve called Snowflake, and another famous tiling, pinwheel tiling, and this is in Australia. Let's see. So I kind of okay, I kind of lost my goal. I'm just talking random. Okay, nobody's. So let me finish giving you a description of this article. So this article, first of all, give you a introduction, a survey of all different kind of different kind of math artwork. Okay, then you have fractals. And you have plotting functions. These are functions of nuMQ on a unit disk. So I don't know what is nuMQ, and this is plotting of complex function. Then you have tilings and patterns. Okay, Celtic knots. Very fascinating, because Celtic knots, historically, it's just a cultural, decorative artwork from northern Europe, Scandinavia. Those people, their artwork, their cultural artwork. But if you study it mathematically, so it's part of knot theory and linkage theory. So if you look into and knot theory has a very interesting history, because in the beginning it's kind of, it's about knots, right? Like, if you don't know about math, you think, wow, yeah, knots. So they are, if you are a Boy Scout or something, you study this. It's very interesting. for a lot of people. But it's surprising, it's amazing that this is actually a proper subject of mathematics, very deep, okay? And it, in the beginning, it arose because people wanted to study quantum mechanics. I learned about the history from Stephen Wolfram's talk. So apparently people wanted to study physics, model the quantum mechanics or something. Then they thought that, the space, at some level is made of knots. So you have to study all the possible configurations of knots. So that's kind of the origin of the history of knot theory. Let's see. We can check history here. Archaeologists have discovered knot tying, blah blah blah. Okay, that's a different. But anyway, so hyperbolic geometry, topologist. Yeah, there. So in 1860s, Lord Kelvin's theory that atoms were knots in the ether led to Peter Gundry's creation of the first knot tables for complete classification. That is, I would claim, this is the beginning, the beginning of knot theory, like Stephen Wolfram told. So this is the first time in 1960, people started, they want to have a classification of all different type of knots. That's one thing mathematicians study, and this is part of a classification is a big type of activity in mathematics. So it's amazing, so when you study physics, you think that atoms were knots in the ether. Ether is a non-existent thing. It's a old idea that turns out to be silly. But one thing leads to another. Then we started to have knot theory, which is a complete, now today is a complete branch of mathematics. You study knots. And knot theory. Then you have ties to geometry, to topology, to group theory. Like the typical how math is very very advanced. I mean, but knot theory you can study by yourself. Actually, you don't need calculus. It's kind of part of a discrete mathematics, like I talked about last time. So in my professor friend's project, 3D Explore Math Virtual Math Museum, you can see several of the interesting knots. For example, this one is called let's see. Oh yeah, this is actually JavaScript. Oh yeah, you can turn it. Fantastic. This is created by Kasia Herman, who is the world's one of the top expert in differential geometry. And it is he who created most of the minimal surfaces. Because he's one of the top expert in minimal surfaces. German guy, Hermann Kasia. You can see if you click around. This is written by him. A friend. He taught me a lot math. So, but you go up. So, but he also do kind of interesting other math things. Not this is not really his focus of study. But anyway, so he wrote this. Let's see. We can. What is this? This is the size. So this is inner radius. This knot is called torus knot because it can create it. Imagine it's a line going around a donut. So that's why it's called torus knot. So let's change this. Okay, so you can change. So you can change. That thing. Anyway. Okay, back to knots. Many things interesting about knots. And here is a curve, Vivian curve. Okay. So let's see. So back to Celtic Knots. So originally it's a decorative arts, but if you are a mathematician, you look at this. You might look at from a different perspective. That is knot theory and link theory, linkages. Now, braid is called braid theory. Okay, let me show you. Search for BRAID. Okay, braids. Do they have a link? They do. Wikipedia is the great resource. So here is the braid theory. You can see. So this is the mathematician study of braids. So it's kind of, so you guys programmers, these topics are something you would be interested. If you are a beginner, like what do I study? How do you go about studying math? What made you interested? So I'm telling you that braid theory, knot theory, is something you can go to, and group theory. Okay, you don't need calculus, because typically you go to a university, it's calculus, right? And calculus, you might think, oh, it's boring. It's trigonometry. It's like, but here, so you have braid theory. Let me show you some other thing about braid theory, because it's let me give you some incentives to go into braid theory, because you read Wikipedia, it might seem boring, but let me entice you with some pictures. Okay, why braid theory? Why, for example, I myself is so fascinated. Why it fascinates me, why do I want to study braid theory? So for example, knighting. Knighting is again a human artifact, very ancient, 2000 years old or something, or even more. So you see this beautiful, amazing, weaving and stuff, cable knight. So women do this, right? It used to be your mom or your grandma, but today is lots of these are done by a machine. But anyway, look at the intricacy. Imagine even this is a puzzle. How do you possibly figure out, which, how the thread go, where it goes, so that you form this pattern? How difficult, imagine. There's such a incredible and beautiful, human creativity. This wasn't invented by a mathematician, like a mathematician sits down and designed this. No, it was, after centuries, trial and error, almost like, all the mostly women, moms, they created this amazing thing. And here's a more elaborate one, cable. So it's called cable knighting. And then look at this one. Okay, this is again something a bit different. This is a tablecloth. Okay, now but look at the intricacy. Okay, so it's magnified, so you can see. You probably have seen this in real life. Amazing. To me, it's just amazing. How is it made? And more so, how mathematically, how where does the lines should go under or over to create this coherent one piece and pattern. So, and then you have the Chinese cultural stuff called Chinese knots. Okay, it's a thing. Like today, if you are American, you probably heard of origami. Or how do you pronounce it? Origami. The paper. Artwork made by paper. And so these things are kind of similar, but it's a different. And also, there's a hyperbolic, surface quotient. Amazing. So amazing. Okay, so let me show you. Yeah. So braid theory. Okay, so that's you might study braid theory. Begin by go read up Wikipedia, braid theory, and knot theory. Okay. And okay, so let me go back to my article, Algorithmic Mathematical Art. So first of all, a survey of all the different artworks: surfaces, polyhedron, then curves, plane curves, then geometric process. Okay, so we have inversion, but also you can have projection from higher dimensions to 2D to a plane. This is one such example. So it projects higher dimensional spheres to a plane. Yeah. So, and also when you watch this in animation in real time, it's amazing. I don't know. I've seen this before, but I think it's, if you look around, you'll find it. You can see this picture in animation. So what you are actually seeing is a projection from a higher dimensional sphere into a plane. Yeah, I don't know. You might search for it. And plane transformation, fish lens or kind of thing, and L systems, turtle graphics, fractals, recursion, artwork made out of recursion. Then you have plotting function processes. Okay. Then you have Celtic knots and braids, and this is a, I believe, Islamic style kind of artwork. And you have weaves and that patterns, and this is a modern thing. Penrose Tiding also, the history of Penrose Tiding is amazing. Okay, if you have not yet, go read it up on Wikipedia, the history of Penrose Tiding. Then you have hyperbolic tidings or some other hyperbolic geometry. Those. And then you have computer generated geometric tiling. Amazing. If you look at this in detail, you see some goes up, some goes down. So it's a knot. It's a knot or linkage braid network. However, each of the weave, each of the line, they must be positioned in certain way so that you form stars. It's quite amazing. So that's why I find this amazing. This one is made by Nodplot.com, which is ancient. This website is one of the most popular around 1997. Okay, when I had my website, this like award-winning, all the this history. So it's internet history. So this website is one of the top visited website around 1998. Okay, late 1990s to even up to 2005, because he has lots of knotworks. Today you look at this kind of city, it's small, small images, font is too small, there's no CSS, there's no JavaScript. Yeah, because the web technology changed. But back then, this is like a great great website. And in fact, your whole screen is no more than this picture. That's your whole monitor is just that big. That's how things are. So anyway, so that is from this side. So okay, so you have knots, then you have fractals proper. Okay, fractals. Now again, if you have not studied, this is part of complex analysis. Okay, I'm trying to get you guys to introduce you to mathematics. Because myself, I'm mostly self-taught, and it took me like a decade to actually begin to know what are what. I'm not a math professor, so I don't really know that deep, but I can, for you programmers, I can give you kind of like a guide and telling you what is about. So if you want to study fractals, this kind of thing, you want to start to study complex analysis. Okay, that's the branch of the math. That's the name of the branch of math. Mandelbrot's set. Okay, now I want to also make a rant. Like most of you, my audiences are programmers, right? So in fact, you have seen, if you have seen the fractals on the web, most of them are created by programmers. Okay, so for example, this image is created by a programmer. This image, beautiful, even though it's very beautiful, it's created, here's some more examples. It's created by a programmer. Okay, now these programmers, typically they know nothing about mathematics. Okay, they are just programmers like you and me. Okay, so these programmers, you can learn what it is, how to create this plot, but you don't really actually understand the math. Okay, so why am I mentioning this? It's an interesting phenomenon because almost all the all the fractal images. You have like back then around year 2000s, you have like 10,000 millions of these, very popular. Uh, but however, they are not created by mathematicians. They are just great programmers. So what's the point? The point is that the point. What I'm trying to say is that there's a kind of difference, a big difference between the programmer's mentality and mathematician. Okay, so one thing I'm trying to say is that if you guys are programmers, right? So when you see this, you might start to study it. In fact, you can do it right now, and you started to write a program which generate these images, and very beautiful and very fast, right? I know that because all my friends are like that, you guys. But it's almost always the case. These programmers, even they spend a year or two in Fractals, they never picked up any real mathematics. Okay, let me go to Mandelbrot said. Okay, so for example, let me go to Wikipedia. Let me tell you, what's the difference between math and programming. Okay, so for example, again, you have these fantastic, actually this is animation. You have these fantastic imageries. These are almost always done by very great, mostly professional programmers. Many of them work at Google or Facebook and so on. But however, if you read Wikipedia, you can see, for example, let me tell you which part are the math. Okay. So definition, Mandelbrot said, is a set of values of C in a complex plane such that critical point Z equals to 0 under the iteration of the quadratic map. Okay, that. Okay, and remains bounded, blah blah blah. So let me tell you, like, I'm trying to tell you. So you have main cardioid and period bulbs, hyperbolic components, local connectivity. So these are math. Okay, but I'm trying to find more of the generalizations. Okay, so so this page, half of this page actually talks about kind of superficial things. Okay, I want to. Am I getting boring? Okay, so let me go. Let me finish this. And actually, I gotta go. I'm right now. I'm trying to pick out part of this article that is very mathematical, and usually the programmers just ignore it because that's very interesting, because there is certain mathematicians, the way of thinking and looking at things are very different from programmers. Programmers, they get excited by just trying to plot this and make it fast. But however, when to math, none of the programmers ignore it. Like, that's it for them. So okay, anyway, I didn't find the part. I want to find lots of like equations and deep theories. But basically, let me tell you. Okay, Mandelbrot set is one of the most fascinating and arguably difficult and wonderful part about math. It represents, let me show you. Okay, that represent almost like the deepest question about humanity, about the universe. You can find it in mathematics. Okay, almost in a sense. Okay, I mean, this is not in any absolute sense. For example, you wonder about how far, the stars, how many stars are there, how many. Then we understand there are galaxies. Then we understand, you have solar systems. Then you have different other star systems. Then you have then you have star clusters. Then you have galaxies. Then you have galaxy clusters. As we advance in the past 100 years, we know more about the universe, cosmology. Okay, that's one thing. That's one aspect of our wonder. You wonder about life. another aspect is like what's the meaning of life, you know, can we live forever, what happens if we die, things like that. Now, in another aspect, that's mathematics, okay, and fractals, in particular, Mandelbrot said represent one of them. It's like you have this thing that's made out of equations, kind of recursion, and this thing so happens it has this extremely weird, you know, what we call fractals now, self similarity, and you can zoom in and it'll be infinite, it'll be infinite and they'll still be very similar to itself, so that is one of the most incredible, fascinating, the heart why mathematics captures so many people's eternal attraction for humanity, even though it doesn't give you any money. You just want to study, kind of look into. That's what I'm trying to say. And one of the great question about this Mandelbrot set, if you look at the definition, let's see if we can find the definition. This article is not very okay. Formal definition. Okay. Yeah, so here is the formal definition. Okay, now one of the question is whether this set is connected. It's like it's part of the question in topology, and that question is just that's very deep. Okay, you see, I'm trying to find now I remember someone proved that Mandelbrot set is a connected set, and that's not easy. I remember somehow it doesn't show up here. I remember I read it on Wikipedia like maybe 10 years ago. Compact set, closed disk, and so on. So disconnected. So who was it? Okay, this guy. There also exists a topological proof of the connectedness that was discovered in 2001. So yeah, so this kind of thing. These things, okay, so it shows it's connected. Yeah, so here let's look at that link. Okay, so yeah, okay, so this page is a general discussion about what it means to be connected. But anyway, you read, you'll find the name, who was it first proved it, and things like that. And let's look at Jeremy Kang. Okay, who is this guy? Mathematician. Okay, Jeremy Kang and Vatmar something. So this is American mathematician. He works on hyperbolic geometry, Raymond surfaces, and complex dynamics. Okay. So yeah. So anyway. So back to so we talked about fractals. Okay. Mandelbrot said the wonders of mathematics, the deepest attraction of the universe. And back to my artwork. My algorithmic artwork page. So then you have higher dimensions. This is a higher dimensional regular polytope, okay, which is a polyhedron, but regular polyhedron, but in 4 or 5 or 6 dimension. You project it or you slice it into 3D and it becomes like that. Okay, he's got this. Most of these people I've contacted, or emailed in 1990s or 20s. They have a website, but unfortunately it's written in Java, which is dead today. So you cannot run it. You have to install Java and do stuff to get it to run. Anyway, so this is a slice of a higher dimensional thing into 3D. And then you have this fascinating this one by Jeff Weeks. Okay, he's a cosmologist. Okay, he's a physicist specialized in cosmology. I went to his lecture one time at UC Berkeley about 15 years ago. He's talking about the shape of space. Okay, so you can go to his website and you can download a program for Mac, for Windows, for iOS too, iOS these days. So he's got you go to his website, he's got quite a few fantastic he's got quite a few fantastic programs written for geometry. Okay, so Jeff Weeks. Okay, and back to my article. So actually, my article is long. I haven't started to talk about. Then okay, so you have higher dimensional space. You have fractals, which is different type of mathematical art. Then higher dimensional space. Then you have evolutionary programming. Now this is the famous Stephen Wolfram's cellular automata. It forms this kind of thing. Also, again, fascinating computation. The nature, if you are a programmer, you'll be fascinated by the nature of computation. What happens if you create a random program and just let it run forever? What happens to it? What kind of what types are there? What's their behavior? That's what Stephen Wolfram, his interest, his primary focus. And so that's called cellular automata and including other systems. Then you have Escher. Okay, Escher, you familiar with? Then you have the transformation, the how they call this. Okay, Escher is probably the first one to create this, but now it's popular. Now there's a guy, a mathematician I'm kind of acquainted with. He's a Canadian. He have done project and thesis about this. So and he has also written a program that tells you in general how to do this kind of gradual transformation. Okay, so you can see. Okay, I gotta go. My alarm clock come on. So this is Escher's gradual transformation from one shape to another. It's called, I believe it's called Parquet deformation or something. Maybe they have a new name these days. Anyway, so the first part of my article is about a survey of different kind of type of mathematical art. Now the second part, I define what constitutes an algorithmic mathematical art. First of all, I talk about what is mathematical art. For example, some of them are not mathematical art, which a lot of programmers love. Okay, I despise. For example, ray tracing. If you are a programmer in my circles, if you love C programming language, C++, Rust, int, float, Java, long, double, short, core stack. If you are into these kind of things, you love this ray tracing, because everywhere you'll see this type of people talking about ray trace. Now that is not a mathematical art. Okay, that in my definition, this is not mathematical art. Okay, this is just a computer generated image. Okay, so let me show you some other examples. That's not mathematical art. Okay, anyway, I gotta go. So my article's too many. So anyway, I want to tell you. So I give you a definition. So what is mathematical art? Mathematical art is a art work that has a mathematical structure. Okay, that's inherent in it. Okay, if you look at this artwork and if there's a mathematical structure, now then it's mathematical art. For example, this one, obviously this is the structure, it's a sine, it's made of sine and cosines. Okay, and this one, it's a Raymond surface. It has many properties. Okay, it's a minimal surface. That means okay, I'm not going to explain what's a minimal surface, but anyway, and this one, for example, it's based on the symmetry of octahedron. Not octahedron. Dodecahedron. Okay, symmetry of dodecahedron. A very mathematical structure. Okay, same thing for all these polyhedron. And this one is, again, it's a solution to embodies this equation, so it has mathematical structure. Similarly, for this inversion of circles or projection of higher dimensional circles or spheres to 2D, they all have mathematical structure. And this transformation of the fish eye lens, is a transformation of the plane. Very mathematical structure, because how it transforms the plane is very regular. And this also mathematical structure because it's a recursive, and the whole graph is made of a single line. You can see I created this. The whole thing is made of single line. So in that aspect, it's kind of interesting. And okay, so all of these have the artwork itself, the visual artwork itself has a inherent mathematical structure in it. Okay, that's a key thing you need to remember. So if that is true, if the artwork has a inherent mathematical structure in it, then that is a mathematical artwork. So same thing can be said for these fractals or Newton fractals. This is a Newton, so-called Newton fractal, because it's the graph of trying to find the root of an equation. And this is a Mandelbrot set defined again by a recursive formula. So this is actually a visualization of a recursion of a math formula, a function. And again, all these two. So this is the shape of space. This is a higher dimensional polytope or regular polyhedron. Again, okay, so all these. So and again, if you look at Escher's artwork, for example, this one, it's very it's a why is it mathematical artwork? Because it has a inherent because it has a math structure embedded in it. Okay, why? Because can you recognize these four circles symmetric in the middle? But however, you also see these four yellow circles. They kind of in a pattern. Then this pattern repeats. So you have a blue circle, blue circle, blue circle, blue circle, and then you have a red circle. It kind of repeats forever, inwards or outwards. So that's a inherent mathematical structure. So this one qualify as a mathematical artwork in my definition. Okay, and this one the same. Why is it math? Because you have two mathematically defined curves. This curve is called equiangular spiral. I talked about it the other day. Okay, so that's mathematical. When artwork has a mathematical structure in it, that's a mathematical artwork. But not. So that's why this is not artwork. This is not a mathematical artwork. Okay, and sometimes you'll see a bunch of others. Let me show you some others. Okay, that's not mathematical artwork, but somewhat popular too. Let me show you. Okay, so go to my Professor Friend's website. Then you can go to math art. Okay. So this artwork. Okay, these are math artwork. Okay, these are. But however, some of them I don't consider them to be. For example, this one. They try to mix fractals with some kind of humanistic touch. Okay. Okay, this artwork. Okay, so that's fractal art. Okay, so you see, they try to mix mathematics with you started to do some painting on it. So I don't like. I think these do not constitute mathematical artwork. In fact, I don't like them. I don't like them at all. Then you have Paul Brook is also very famous. He is a very great geometric programmer. But this one, if you look at it, is it mathematical? Does it have inherent mathematical structure in this artwork? I wouldn't say so. Okay. Does this one? Maybe. Yeah, actually it is. This is Calabi-Yau surface from string theory. Okay, so you can consider that to be a mathematical artwork. Okay, inverted Trott tiling. Okay, this also qualify, I guess. Okay. Actually, his work mostly qualify, but I want to show you some of them that's common, but very not mathematical. Okay, we started to see them. You see, so yeah, it's artwork, but this is not a mathematical artwork. Okay, it's based on some math ideas. Okay, this one again, it's it's an artwork, but I wouldn't call it a mathematical artwork. It's just a artwork that's with heavy math influences. You get my idea, I think. And these ones, in the same way, I don't consider it mathematical. Okay, so that's mathematical artwork. That's my definition of it. Now let me go back to my article and finish explaining my article. Okay, so that's how I define mathematical art. That's the first part, very important. Now the second part is even more important. So what do you mean a algorithmic mathematical artwork? Okay, so this article I'm trying to define the concept. I'm trying to define the concept algorithmic mathematical art. Okay, so first of all, I defined what is mathematical art. But what do you mean by algorithmic? Okay, that takes some time to explain. So, but I gotta go. But basically, so suppose imagine you have this artwork. Okay, this one is Escher, very famous, and it's very beautiful, and it's also mathematical because it's 100% symmetric. It's purely with a pure mathematical structure. That means with this artwork, there is an algorithm like embodied with the whole thing. I mean, like the whole thing can be generated by one single and simple algorithm. Okay, that is what I mean by algorithmic mathematical artwork. That means you have to write a program. If you write a program to generate this work, your program may not be a algorithmic mathematical artwork. If your program do not capture the inherent algorithmic process that is in the artwork. For example, if you draw this one, if you are like Escher, you started to paint it, for example, or if you make a photocopy of this and you started to write a program that start to draw each pixel, from the top to the bottom. So you obtain a computer program that can generate this picture. However, it's done by drawing pixels per pixel. So in your program, it has no, it doesn't have the beauty of, it doesn't capture the algorithms at all. So if you do it that way, then that program is not a algorithmic mathematical art. Okay, even though the result is the same. That is essentially my point. So you can write a computer program. Here's my point. You can write a computer program to generate every single one mathematical artwork on my page here. Okay. However, your program, the algorithm used in your program, doesn't matter what programming language you write it in, C, Golang, C#, Scheme, Lisp, Mathematica. Okay, your program must use the algorithm that inherently capture the embedded structure of the artwork. If you do it that way, your program is I would say algorithmic. Okay. Thank you for watching. If you like my stuff, donate Patreon. Okay, I gotta go. I gotta go. Thank you. Bye, guys. Patreon me, PayPal me. Don't forget. I must mention that.